Morning, guys. Hey, listen, today we're going to, at about 9:40, I'm going to give you your quiz. There are 13 questions, multiple choice. I'm going to have, right now we'll have maybe 15 minutes or so to review. I'm going to go over all the topics. And then if y'all have questions, I can answer them as well. But I'm just going to sort of review the major topics just to jog your memory. All right, so Chapter 1. You need to know the difference between models, theories, and laws. We talked about models, how they were analogy or something that describes something. After many years of testing them over and over again, they become a theory. All of these are created with experimentation, or rather are followed by experimentation and observations. And then after even many years, sometimes even centuries of holding to these theories and showing that they're true and over and over and over again, then they become a law. And a law is considered to be immutable. It's unchanging, and it's entirely correct. We talked about the different realms of physics. Classical is large and slow. Fast and large is the study of relativity. So we had classical. That's sort of what we do in here. That is large and slow. And over here at fast, we have relativity. Then we had quantum, which is small and slow, like the study of atoms, for example. And then relativistic quantum physics. You should have this in your notes. Relativistic quantum. You need to know the units, length, mass, and time, the different systems. We use the MKS or the SI system. That's meters, kilograms, and seconds. You also need to know the standards for each of those and what makes a good standard. Remember, we have 3 criteria for making a good standard. That is that it is accurate, it is accessible, and it's unchanging. It's accurate, meaning you get a good standard. You know exactly what a kilogram is, for example. It's accessible to everyone, so not just the French have it. And then also that it's, what was the other? Oh, unchanging. And one example of a changing standard is like that for the kilogram. Remember, the kilogram is losing mass, and so they're changing to this new system. You also need to know what are the standards for the meter, kilogram, and second. For the meter, it's the distance that light travels in a particular amount of time. For kilogram, it was that cylinder in France, although we're making this transition to this sphere of silicon. But right now, it's the cylinder in France, this metal cylinder. And then, what was the other one? Time. It's the cesium atom. It's the frequency of the cesium atom. All right, so you need to know what those 3 standards are and what makes a good standard for measurement. You need to know these metric prefixes. You will have a question or 1 or 2 questions where you have to convert units, and you need to know these metric prefixes. Did I give y'all mega? Did I say you had to know mega? Yeah. Okay, so mega, kilo, centi, and milli. That's 10 to the 6th, or a million. This is 10 to the 3rd, or 1,000. Centi is 10 to the minus 2, or you can think of it as 1 over 100. And this is 10 to the minus 3rd, which is 1/1000th. All right, so you need to know how to convert between one unit to another. Like, for example, let's say I want to know how many kilometers or how many centimeters are in a kilometer. So I'd say 1 kilometer equals how many centimeters. You can do that thing that you do. That's not the way I do it. That's okay. You can say 1 kilometer. 1 kilometer is 1,000 meters. And in 1 meter, there are 100 centimeters. All right, that's based on this for centi. In one meter, there are 100 centimeters. And that gives you, what's that, 10 to the 3rd, 10 to the 5th centimeters in 1 kilometer. All right, so make sure that you know how to do those unit conversions. You'll also need to convert between different systems, like maybe the British say miles per hour to meters per second, or maybe just some random thing like an iPad to measure the length of this file and be able to convert from, well, if this aisle is 25 iPads long and an iPad is X centimeters, then how long is this row of chairs? Right, like that exercise we did in class. All right? This is fast, but we'll come back if you have questions. I'll answer them. That's it for chapter 1. In chapter 2, need to know what displacement, velocity, and acceleration are. You will have those equations that I put online, and I had the equations for, what did I have? Velocity is distance over time. Average acceleration is velocity over time. And then I had those the other two kinematics equations, which was S equals V initial times T plus 1/2 AT squared, and V equals V initial plus AT. Don't bother memorizing them. I'll give them to you, but you need to know when you're reading a problem, like in the homework, and several of the quiz questions have come almost basically from the homework, very similar. Being able to read through those questions like the ones we did in class and pick out, well, this is the initial velocity, and this is the displacement, and this is the time, okay, and pick out whatever it is that you need to know. So it's sort of problem-solving skills and being able to pick out the correct information. So you will have some kinematics questions where you have to solve for either the displacement, the velocity, or the acceleration. All right? That's not a surprise, right? Okay, good. They'll be very, very similar to the homework, also similar to the examples we did in class, which are similar to the homework as well. You'll need to know how to describe the graphs of motion. There's an ant on my thing there. So for example, if I have a distance versus time graph that looks like this, the slope of that graph gives the velocity. This has a positive slope, so I have a positive velocity. Is that velocity increasing or decreasing, or staying the same? It's staying the same. The slope gives the velocity, and since the slope is constant, it is constant velocity. On the other hand, this graph, S versus T, which looks like this. I remember this is the same graph that we had when we had the car going down the incline, right? Positive or negative slope here? Positive slope, so it has a positive velocity. Increasing or decreasing velocity? Increasing. It's increasing velocity. It's accelerating. You can look at this. If you think about the slope of this part of the graph, it's very small. The slope of this part of the graph is very large. So it's an increasing slope. I gave you several other graphs. You should look at those. I also gave you graphs for a couple of special cases. That is a ball that you throw up in the air, and then it comes back down to you. This graph, if I were to plot the V versus T, looked like that. Remember, it initially has a big positive velocity. At the top, the velocity goes to 0, and then it has a negative velocity when it's coming back down. All right. What is the slope of this graph? The slope of a V versus T graph gives us the acceleration. And what the slope of this graph is, positive or negative? It's negative. This is a negative slope. This is a positive slope, negative slope. I think this could be a dance. Like every year I do this, and I think they negative, the slope dance or something. Y'all should work on that. So what is the value for this? If this is a ball that I throw up in the air and then it comes back down, what's the value of the slope for this graph? Going into the next section. It's a particular number. What is it, Sam? Negative 10 meters per second squared. And that's the acceleration due to gravity. And then that's the final section on this. And they're just kinematics problems, just like we did with the cars and the balls and all that stuff, except now the acceleration won't be given in the problem, but you'll know that it's negative 10 meters per second squared. All right. Any questions about material? Yeah, what's your name? Courtney? It's, you round off 9.8 to 10. Well, in the quiz, it's multiple choice. I use 10. Yeah, it's easier. So if you're fairly decent with numbers, I don't think you need a calculator necessarily, but you're welcome to use one because you will be working with numbers. So, all right. What else? Any other questions? None at all? You'll feel comfortable with it? You'd rather take it right now and just go, right? Yeah, no, I'm sorry. We need to hang on about 25, 30 minutes. We're going to move on into Chapter 3. Remember, I've already put up the homework for Chapter 3. Did y'all look at the videos? Are they useful for you? Yeah, okay. Well, I'll keep doing them for the rest of the semester. That way, it just allows you a place to check to make sure your answers are right, and if you get stuck on a problem. But I don't want to discourage you from coming to see me, because often it's a lot more effective if you have trouble, to come talk to me, and then I can sort of feel what your problem is, and we can work on it together, okay? So even though you have these videos, please still come see me. Chapter 3 is on forces. We're going to look at Newton's laws. A force, and this is like a second grade answer, but it's a good definition of a force. A force is a push or a pull. And there are lots of different ways to exert those forces, and we're going to look at some different types of forces in this chapter. It's a force. A force is a push or a pull. In particular, this push or pull will cause an acceleration. All right, so it'll be different from something that's just moving at a constant velocity. We're going to define a force, in particular a net force, that is, I have a force that's in a particular direction that will cause an object to accelerate. All right. So a force is a push or pull that can cause an acceleration. And Newton's laws, Isaac Newton, describe the relationship between force that's one word. It's not like a relationship, it's a relationship. All right, the relationship between force and motion. Do you know, by the way, Newton is known for these laws of motion, but do you know what else Isaac Newton invented? And this is pretty cool. I know. It changed your life. Who knows what Newton? Isaac Newton invented calculus, and calculus allows for all sorts of, and it allowed, for building this building, for example. It allowed for engineering that we couldn't do 100 years ago, or 1,000 years ago, or several hundred years ago. So calculus literally changed your life. It allows for your banana phones that you keep in your pockets, and it allows for, like I said, building science, all sorts of cool stuff. So Isaac Newton also invented calculus. He had 3 laws. The first we call the law of inertia. Now, before Isaac Newton, there was this typical view that was put forth by Aristotle. And Aristotle thought that objects had a natural state, and objects always wanted to be in that state. What do you think that state was? When you look around and you see objects around in this room, wherever you are, what are they typically doing? Are they moving or just sitting still? What are they doing? Think about all the objects that you see. Are they moving or at rest? Yeah, they're at rest, right? Leaves on the ground, trees, all of y'all are at rest right now, the chairs. Most things, if you look around, they're at rest. So Aristotle said, aha, every object has a natural state, and that natural state is at rest. And he actually described that any time that something went out of rest, that when it moved, that was very violent. It was like removing it from the womb, removing it from its natural state. And it was just a very violent act to remove it from this natural state of rest. But Isaac Newton had a much different view that really sort of radicalized how we look at motion. He said that any body, that any object will remain at rest and that's not different from Aristotle, but also will remain at rest or in motion in a straight line with a constant velocity unless acted upon by an outside force. So Isaac Newton would say that if you have something, let's see, I don't have my tennis ball, but if you have something and you throw it, what's going to happen to it if there are no forces acting upon it? It's going to go, and it's going to go for how long? It's going to go forever. That's what Isaac Newton would say, and that was his first law of motion, the law of inertia, that if you have an object, its natural state is neither rest or in motion. Its natural state is whatever it's doing right then, unless a force is acting upon it. So in order for an object to change velocity, you have to have a force that acts upon it. That's the law of inertia. This property of objects, inertia, is a measure of their mass. What's easier to move? Like if I have a huge crate or I just have a little bitty tissue box, what's the easier thing to move? The little bitty thing or the really big thing? The little bitty thing, right? The one with not very much mass, and that's because it doesn't have very much inertia. So something that's big that has a lot of inertia is very difficult to move. It requires a lot of force to move, and something that's small and without very much mass doesn't require much force at all. I want to have a little video, and then I'll show you the second and third. But this video is from a PBS show about circuses. You ever seen this? I forget what it's called. It's the circus or something. But they talk about the physics of these little dog shows they're doing. It's kind of fun. Let's see. All right, so the second law, the first law is the law of inertia, which is a measure of this mass. The more mass you have, the more difficult you are to move. And the natural state for an object is just the state that it's in, whether it be in motion or at rest. Now the second law describes the relationship between force and acceleration. And it just says that the acceleration is equal to the force over the mass. All right, so if I have an object and I exert a certain force on it, then that's going to cause a certain acceleration. What if I exert the same force on a small mass and on a big mass? Which is going to feel the greater acceleration? The small mass or the big mass? That is, if I make m here very small, what happens to the acceleration given the same force? Is the acceleration big or small? It's going to be big. If my mass is small, if I make that number very small, then that causes my acceleration to be very large. All right? It's like, well, never mind. Often we see the second law. This is the way that Newton wrote it. Actually, he wrote it a little bit differently than that, but basically like this, that the acceleration is equal to the force over the mass. But usually when we write it, we'll say that the force is equal to the mass times the acceleration. We'll have a few homework problems that are related to this that use this relationship between force, mass, and acceleration. Now, this force is going to be our net force. It's the sum of all forces. And actually, more in particular, it is the vector sum. So let's say that I have a rope, right, and I have one guy pulling on that rope with a force, say, of 100. The units of our force is newtons. I'll go and write that. We'll see that in a second. And then I have another guy that's pulling on the rope with a force of, say, 50 newtons. What is going to be the vector sum of all of my forces? You had a homework problem sort of similar to this in Chapter 2, but not forces. What's going to be my net force that's acting on this rope? I have one guy pulling with 100 newtons in this direction, and then I have another guy pulling with 50 newtons in this direction. So what's my net force going to be? It's going to be 50 newtons. And what's the direction of it going to be? My guy is pulling in this direction with 100, this is to the left, and then my other guy is pulling with 50 in this direction. So what's my net force? All right, it's going to be negative 50 to the left because the 100 newtons is greater to the left. All right, we'll get into that a little bit. We're not going to do a whole lot of vectors, but we'll see it a little bit. And when I talk about Newton's second law, we're always referring to the net force, or the vector sum of all the forces. All right. The third law is the action-reaction, or describes action-reaction. You may have heard of this before. And it says that when one body exerts a force on a second body, the second body exerts an equal and opposite force. On the first body. When we're talking about contact forces, that is forces between two objects that are touching, this should be fairly obvious. Let's say that I have a chair. All right, I'm sitting in my chair, slouching a little bit. I'm sitting in my chair, and I'm exerting a certain force down onto the chair. Right? My body exerts a certain force down onto the chair. And if you can imagine this chair, well, you can't imagine because you're sitting in a chair right now, that chair is pushing back up with a force that's equal but opposite to the force that's pushing down. Likewise, I'm just standing here. I weigh about 700 newtons. That's my weight in newtons. And I'm pushing down on the floor with about 700 newtons. What is the floor pushing back up on me with? Okay, well, equal and opposite. So yeah, 700 newtons in the opposite direction. All right. What would happen if the floor was not pushing back up on me with 700 newtons of force? What would happen? What would happen? I would go down. I would be accelerating downward because then I would have a net force that would be down, and I would crash down through the floor and into the foundation of the building. All right? So that should be fairly obvious to you that if I have a contact force where two objects are touching one another, then the second object is going to push back with the same force that the first object pushed on. Does that seem obvious to you? Yeah, I think it probably wasn't real groundbreaking for people then, but Newton also said, and we'll talk about this later in this section, probably next time, but Newton also said that if you have field forces, and this is still kind of baffling, this also applies for field forces. A field force is a force that doesn't require contact. There are basically 4 field forces. We'll talk about 2 this semester. The first one is the gravitational force, and then the second is the electric force, the force between charges, which we'll get into later in the semester. The gravitational force doesn't require contact between me and what other object? What is the gravitational force exerted by? What causes me to stay on this planet? What? Okay, yeah, the gravitational force, but what is the gravitational force caused by? What phase? No, not magnetic fields. That's a good guess, though. What's it caused by? It's a property of mass, that if you have 2 bodies of mass, they're going to be attracted to one another. And this is shown on smaller scales, too. Like there's literally a force between every one of us, a gravitational force that's attracting you towards one another. It's very, very small. You can't feel it. Do you feel any forces acting on you right now? Yeah. So it's a very small force, but it's measurable nonetheless. And there was an experiment back in the early 20th century that actually measured that force. Between 2 just sort of steel balls. They measured the force between them. So anyway, there's this force that's between you and me and between you and all the other folks here that doesn't require any contact between you. Doesn't that baffle you? That there's a force acting between you that doesn't require any contact? Who does that baffle? Nobody? Okay, thank you. It's a timer, yeah. It doesn't require any contact at all. So what causes that force to be applied? All right, so for example, I have a person here, and I have a person here, and they both feel a force that's equal and opposite. Okay, but there's no contact between them. What causes this force? We don't really know what causes the force is the thing. Like even today, we don't really understand how the gravitational force works. But we're really starting to make some inroads just in the past couple of decades into understanding how this works. I have a little video I want to share with you. It's just for your own interest. But in short, I want you to know that it's thought that this force is conveyed by these particles that are called gravitons. All right? So this force is conveyed by particles called gravitons. Let's watch this little video. It talks about Superman and how Superman can fly. All right, so actually, I don't know if y'all know about Superman, but it used to be that Superman didn't fly. Did y'all know this? What did Superman do? No, he didn't fly. Yeah, he didn't fly. It used to be that he couldn't fly. What did he do? Vision? Yeah, like X-ray vision. Yeah, we'll talk about that later. No, he used to not fly. He used to just leap tall buildings, right? He was just really strong, and he could leap over tall buildings. But then in later versions of Superman, he actually got to where he could fly, because, I don't know, that's more romantic to take Lois Lane out flying or whatever, than to just leap tall buildings. But so now people, well, Superman's imaginary, right? But it could be that one day, if we ever actually learn what these gravitons are and how to harness them, that perhaps we could fly like Superman. And that would be kind of cool, wouldn't it? Yeah, I think that would be neat. Um, there's an experiment right now in Louisiana. It's actually in Louisiana and in Washington. Are y'all familiar with it? It's trying to determine or to detect these gravitons. It's called LIGO, the Large Interferometric Gravitational Observatory. No, it's basically this huge piece of concrete, and they're trying to detect what happens to this big piece of concrete when these gravitational waves go through it. It's very sensitive. Like it can pick up waves lapping on the Gulf Coast. This is up in northern Louisiana, and trucks driving by on the road. But it's trying to detect these gravitons or gravitational waves that will come from these huge cosmic events, like black holes colliding with one another, or a hypernovae or a supernovae when a star blows up. So that could be very exciting in the next 50, 100 years as we learn more about what gravitons are and how we can use them or how they might impact our lives. That could be like the next big thing. All right. Um, all right. I think that we'll stop there. So go ahead and put your stuff away.